Okay, so now I want to take a little time to talk about combinations of capacitors in circuits. So for instance, let's just put two capacitors in series in a circuit and see how we deal with those. But first, I was wondering how many elephants you could get into a taxi. I think it's 4, right? You have 1 next to the driver and 3 in the back. Okay, so yeah, okay. I'm not even going to comment on that joke. So let's say that we have a circuit with 2 capacitors. Let's say we have a capacitor of 1 microfarad and a capacitor of, let's just say 2 capacitors of the same, 1 microfarad each, and a potential difference of 6 volts attached to those capacitors in series. So how do we know how much charge goes to each capacitor? How do we know how much energy is stored in each capacitor? Well, first of all, you can use Kirchhoff's loop rule, and you know that if you go around a loop, delta V must equal 0. And so that just means that if you gain 6 volts here, you must lose 6 volts here. They're the same, so it's pretty clear that this one's going to be 3 volts and that one's going to be 3 volts. In that case, that's easy. We don't have to do any math. 3 volts each. So if there's 3 volts on each capacitor, then right, so the voltage across each capacitor, let's give these capacitors numbers. Let's call this capacitor number 1 and this capacitor number 2. Voltage across capacitor 1 is 3 volts. Voltage across capacitor 2 is 3 volts. And so therefore, the charge on capacitor 1 is equal to C equals Q over V, so C delta V, which is 1 microfarad times delta V, which is 3 volts. It's not 6 volts, right? It's the voltage across the capacitor, not the voltage of the circuit. And so that is 3 microcoulombs. So the charge across each is 3 microcoulombs because they're the same. So there's 3 microcoulombs on each capacitor, because we're just going to find that Q2 is C2 delta V2, which is 1 microfarad times 3 volts. It's 3 microcoulombs. Okay. So notice that if there was a single microfarad capacitor, it would have taken all 6 volts, and it would have 6 microcoulombs. So less charge moves here. Right, so we've got 3 microcoulombs of charge going this way and minus 3 microcoulombs of charge going this way. Let's redraw this circuit. So look and see what happens microscopically, right? Microscopically, what happens, we can't see this happening, but that's what I mean by microscopically. Because each capacitor is charged to 3 microcoulombs, what that means is it's got a plus 3 microcoulombs on one plate and minus 3 microcoulombs on another plate. And so what I'm showing here is that in order for that to happen, the battery only has to supply 3 microcoulombs, right? That's bad color. The battery only has to supply 3 microcoulombs going that way and minus 3 microcoulombs going that way. That's what gives us this and this. But where do the other 2 charges come from, right? I'm using some funky pink color. Where do those 2 charges come from? Well, that's just a charge separation that is induced by the charge that comes from the battery. So the battery has supplied minus 3 microcoulombs to the right-hand side of the right capacitor and plus 3 microcoulombs to the left-hand side of the left capacitor. And what that does is it induces a charge separation on the inside 2 plates, right? These 2 plates are not attached to any part of the battery. So they're neutral. And so we just induce a charge separation between them so that you have equal charge on each plate. So the point being here, one of the points being here, that the battery actually provides less charge than with a single capacitor. Therefore, also note that it must take less energy, but then with a single capacitor, 1 microfarad. So what would the equivalent circuit of this be? If this was a single circuit, If this were a single capacitor, right, we've got the equivalent capacitance. and with 6 volts potential difference, then the equivalent means that the battery wouldn't see anything different. So the battery would still supply plus 3 microcoulombs and minus 3 microcoulombs, right? So this capacitor would have 3 microcoulombs on it, and so the equivalent capacitance must be, therefore, the equivalent capacitance must be Q over delta V, 3 microcoulombs divided by 6 volts. Sorry about the mess. The equivalent capacitance is equal to 1/2 microfarad, 0.5 microfarad. So the equivalent capacitance of a single capacitor circuit that acts the same as a circuit with 2 capacitors in series has a capacitance that's less than each of the capacitors. So the capacitors don't add. It's not like 2 resistors in series. If these were 2 resistors in series, the resistances add so that the equivalent is as if is 1 resistor with the sum of the 2. In this case, it is not. That is not the case. Let's see how this works in general. So two capacitors in series, just do what we did in the previous page, but we'll do it with letters instead of numbers. Kirchhoff's loop rule tells us that the sum of the potentials around the loop must equal 0. That's the first line. The second line is just saying, well, then therefore delta V, the potential difference by the battery, must equal to the potential differences of each capacitor added up. I guess I could have written them as potential differences, delta V instead of V, in order to be consistent. Okay, so there, I've written them as delta V's to be consistent. Okay. And we also know that delta V for the equivalent capacitance must be, delta V. So delta V for the equivalent capacitance, never mind that for a second. Let me just do something here. Let's write delta V, let's write it in terms of Q and C. So delta V is, Q1, oh gosh. So I keep on messing up my what's on top and what's on the bottom, right? I'm going to use this fact here, the definition of capacitance, so that delta V is equal to Q over C. Okay, so Q1 over C1 plus Q2 over C2 equals delta V. But down here, for the equivalent capacitance, well, delta V must equal to Q over C equivalent. So we can write for the equivalent capacitance, delta V is Q over C equivalent, where this is Q and this is minus Q. But then what we recognize is that what is Q1 and Q2? Q1 is the charge on capacitance. Q1 is the charge on capacitor 1, and Q2 is the charge on capacitor 2. And Q must equal Q1 and Q2 because the whole point of equivalent capacitance is that the battery must provide the same amount of charge or the same amount of current to the equivalent capacitance as it does to the 2 capacitors in series. So since Q, and so therefore, I'll go to a new page. Okay, so this is the important fact, that the charge on the equivalent capacitor equals the charge on each of the individual capacitors, right? So going back to this page, the whole point that we did with the numerical example is that Q1 went in that direction and minus Q1 went in that direction. That's just Q2, right? Minus Q1. And in that case, that's going to be the same here, Q1 and minus Q1, the whole point of an equivalent capacitance. So Q1 and Q2 are really the same charge, and they're the same as the equivalent, the charge on the equivalent capacitor, in order for the battery to provide the same charge in both cases. Okay, so therefore, so taking the equations from the previous page, for the capacitors in series, we've got that. For the equivalent capacitance, we got that. And the fact that Q1 is equal to Q2 is equal to Q tells us, therefore, that Q1 over C1 plus Q2 over C2. Whoops, that's a C2. That actually, I'm just solving these two together, equals Q over C equivalent. And since all the Q's are the same, therefore 1 over C1 plus 1 over C2 equals 1 over C equivalent. So that is the important key to series capacitances. Series capacitances add as the inverses. Just like, remember, we've seen this before for resistors in parallel, but series capacitance add as the inverses. Okay, so let's just do an example. I have two capacitors in series, and I'm going to ask what is the equivalent capacitance, how much charge is on each plate of each capacitor, and what is the delta V for each capacitor. So let's call this C1 and this C2, and so B and C refer to C1 and C2. Okay, what is the equivalent capacitance? So these are two in series, so the equivalent capacitance A, 1 over C equivalent equals 1 over C1 plus 1 over C2 in general in series. So therefore, 1 over C equivalent equals 1 over 2 plus 1 over 1. Do the math, and you get C equivalent is 2/3 of a microfarad. These were in microfarads. I just left off the units when I plugged in the numbers initially. Okay, so part B, how much charge is on each plate? Well, how much charge is on each plate? How do we do that?